next speaker is Dan Scolnic from University of Chicago, telling us about the exciting times in Hubble constant measurements.
Great. Thanks, everyone. I want to thank the organizers for having me, especially at this time. There's been just a lot of excitement about new measurements of the Hubble constant, and I'm going to try to go over where things are and where everything's are falling, even though it seems like the conversation shifts every week or so. I want to start with a plot that you saw from Elizabeth Krauss about the recent DES results. So this is plotting sigma 8 versus omega matter, and I don't want to show this in terms of something too scientific, even though this relates to measurements of the Hubble constant. But I want to make the point that I think over the next few years or so in cosmology, we're going to be seeing a lot of plots that look like this, where from two different surveys, you see these 2D contours, and there's kind of some region of overlap in the two sigma region from both, and there's just this question of, okay, are these surveys in tension with each other? Is this agreement? Can you really combine these? And DES did this really smart thing, which is they chose what their definition of tension meant before they unblinded. And this didn't quite pass the cut. But then you start thinking that there are these other surveys, and they're also pulling in this direction from Planck. So should we combine with those? And it turns out now that in cosmology, there's all these different bits of tension and hints of tension, and it's unclear now what's real and what's significant. So I want to try to summarize all of that in a map, and I want to base that off of Game of Thrones. So apologies to people who don't watch the show, but this is what I call the game of tension, where I tried putting on all the different cosmology surveys that have put out recent results. I color code them by the type of probe they are, whether it's CMB, BAO, supernova, weak lensing, Cepheid, strong lensing. And this is a kind of lay of the land about how far away different probes are from each other. So I do work on the SHOES team and also for Pan-STARRS. The big story has been tension between Planck and SHOES, but if you kind of try putting them all together, you see there's all these different poles in similar directions. And there's this point earlier about what's a conspiracy versus physics, and that's kind of the interesting question that's being asked here. And are really all these surveys in agreement with our standard model of cosmology? Okay, now I want to focus on the measurement of the Hubble constant, really because it's our best end-to-end test of the standard model of cosmology. We have this picture of the universe where there's dark matter and dark energy, and you combine this with GR, and if you take an accurate picture of the CMB, very early universe, you could infer a measurement of the Hubble constant that we'd see today, a measurement of the expansion rate of the universe that we see today. Now, my team can go ahead and measure what we see for the expansion rate of the universe, and comparing these two tells you how good our measurements are in agreement with lambda CDM. Put another way, if you combined CMB and BAO measurements with an external measurement on H0, like a local measurement on H0, this constrains dark energy, because really you're using the two furthest parts of your lever arm, the most recent measurement and the earliest measurement you can, and you constrain everything in the middle. Okay, so I'll quickly go over results from the SHOES team. That's what I work on with Adam Rees, Lucas Macri, Samantha Hoffman, and many others. I'll then discuss all the new H0 measurements, and if I have time, I'll talk about how we're improving our own measurement to go from basically 2.4% to 1%. Okay, very quickly, there's three steps to measurement of the Hubble constant. Basically, in the first step, you're using some geometric method like parallax to calibrate the luminosity of Cepheids. Then in the second step, you're saying now that we know the luminosity of Cepheids, we'll find galaxies that host both supernovae and Cepheids, and this will allow us to calibrate the luminosity of supernovae. And then in the third step, you say now that we have the luminosity of the supernovae calibrated, we could determine the Hubble constant, because the Hubble constant and the luminosity of supernovae are degenerate. Just a couple quick points about these first two. I show here measuring this first step with parallax. There's really 4 different anchors that we use to provide an absolute distance measurement. In the second step, we do all the Cepheid measurements in the IR. So this really reduces our sensitivity to metallicity, reddening, that they're much more of a problem in the optical. And actually, when you combine when you compare the Cepheids to the supernovae, the scatter is really dominated from the supernovae. So most people point at Cepheids as being the problem if there's a problem with our H0 measurement, but scatter it comes from the supernovae. And now that we've worked a lot on the calibration of the supernovae, the big issue is that we need a better understanding of the physics of the supernovae, progenitors, and things like that. So there's interesting ideas of doing this in the future, like there's this LOX project, a gamma ray project by Richard Miller, and we need kind of things like that to start understanding the physics better, to kind of get down to the sub 1% level. Okay, then in the last step, basically we use the full compilation of supernovae that we have, and I spent a lot of time trying to cross-calibrate all the different surveys. And then the intercept of this diagram tells you the Hubble constant. And one thing that's made a lot of news in this last year is that maybe one way to explain the Hubble constant is that we live in a Hubble bubble or some very underdense region of the universe. We don't see any kind of kink in this Hubble diagram that might go along with it. There's this nice paper by Wu and Hutter that came out that says basically where we are has to be extremely underdense to explain the tension that we see. So I don't find that very credible so far. Ultimately, we produce the distance ladder. So we're calibrating the Cepheids, then the supernovae, and then H0. And this process does all these steps simultaneously. And really what makes the distance ladder so powerful is that if there's some problem with supernovae, it affects both this rung, and that systematic will cancel out. So it's designed to mitigate systematics. Our results were that using the different anchors, we got values of the Hubble constant between 72 and 76. Our best estimate of H0 is 73, and this is 3.4 sigma higher than what Planck has, assuming 3 neutrino flavors and a mass, this mass here. This is less tension than some combination of WMAP, but Planck analyses have shown kind of maybe where some problems of WMAP might be. So in this last year, it's been fairly stressful because our results have gotten a good amount of attention, which means that a number of groups have reanalyzed our results. Overall, I'd say that no one has seen anything that different. So we got 73.2 plus or minus 1.7. There have been a new treatment of the Cepheid systematics or new Bayesian treatments. Overall, they get pretty similar numbers, similar errors. There's one, Zhang et al., that did a blinded analysis of the 2011 shoes analysis. They got a similar mean error, but a bigger error. My take on that is just that they did not treat the systematics of the distance ladder simultaneously, which mitigates systematics. But they basically didn't treat it as a distance ladder, and that's what blew up their error. So the big story is that of the reanalyses, nothing has changed our results too much. Okay, now when our results came out, basically we were here. This was consistent with past analyses of our distance ladder measurement. And Planck was here, and there's this 3.4 sigma tension with WMAP kind of in the middle. After our results came out, these new analyses using the distance ladder came out, basically replacing either the supernova component or the Cepheid component. And overall, so they kind of kept the rest of our distance ladder, just replaced one component. And overall, their numbers and errors were pretty similar. The errors were a bit bigger just because they had to reduce statistics. So that was encouraging. And then what came out is a new strong lens measurement by the Holy Cow team. So this is a low Z measurement, and they came out on the on the high Hubble constant side. And then there were a number of analyses. This is like one by Addison et al. That showed that if you combine BAO plus BBN, so a kind of high Z measurement, that is also on the low H0 side. So what got to be very exciting is that maybe we're actually seeing some real new physics. Something has changed outside of the lambda CDM model, going from high Z to low Z. One wrinkle is that SPT, which is also a CMB measurement, they just came out with their results, and now they're a bit on the high H0 side. So if there is some kind of high Z, low Z issue, this doesn't quite fit in that story. Now, what we had said when we put out results is that to kind of go from Planck to our results, if you think of new physics, there's different ideas to have. You could say non-flat curvature. You could say that dark energy equation of state is changing, or that the number of neutrino species isn't close to 3. So we would find that's like 3.5. Now, there are people like John Beacom that would say basically proceed with caution before invoking another neutrino species. I don't think we're ready yet to say we've figured out all this kind of scatter before we've really hit the level of new physics. But kind of things that relieve the tension the best is certainly the extra neutrino species. The problem is that even by doing so, it makes CMB fits worse. So there's really not anything that kind of makes all these data sets happy. There's not one kind of easy answer. Now to go back to DES, basically what DES is adding to the story is really that they want omega matter to be lower. So this is combined, the Hubble constant versus omega matter. They will pull up Planck's value of the Hubble constant, because this is Planck here. For SPT results, SPT already wants a lower value of omega matter, a higher value of omega lambda. So this will just shore up their errors. So there's all these different polls, and it's unclear right now what it means. Even in the Planck data itself, if you cut on a certain L value, this could move around. So this is kind of based on some work by Addison. Sylvia Galli did a pretty comprehensive review of all this. And you could see, depending on your cut, this can push H0 lower, but if you have all of your Planck information, this is what gives you your H0 of 67. Okay, so in my last couple minutes, I just want to say, how do we then go from a 2.4% measurement to a 1% measurement? Because really, that's pushing this 3.5 sigma tension to 5 sigma tension, and that makes all particle physicists more willing to accept that this is real. So this is kind of a simplified error budget, where from the first step, there's a 1.4% uncertainty. From the second step, there's a 1.2% uncertainty. And from the last step, there's a 0.4% uncertainty. Now, for the first and third step, those are going to get a lot better really quickly. For the first step, Gaia has now come online. They're producing lots of data that they'll release soon. Already, there have been papers out that show that you could use our Hubble constant to predict the parallax that Gaia sees for its Cepheids, and that seems to be in very good agreement with what it actually sees. We're kind of right at the minimum of this chi-squared here. So that first rung of the distance ladder will pretty much get nailed down. And then for the third rung of the distance ladder, I'm working on this foundation survey, which uses supernovae from Assassin. So it's unbiased, and it has excellent calibration from pan-stars, and we could kind of check that last rung of the distance ladder. Really, the issue then just becomes this middle step. So the middle step is where we need to have galaxies that host both Type Ia supernovae and Cepheids, and that means you need to have very local galaxies to do the Cepheid measurements, but you just don't have supernovae go off that often. You basically get one per year in the local volume. So right now we have 19. We just got a lot of HST time to push us up to somewhere around like 30 to 32. Ultimately, we're trying to get to 50, and that's really what will get us to the 1% measurement. As we shrink this down, push this 1.2% down, that gets us there. So it's really not unreasonable to think that even in a couple years, will start scratching sub 1.5%. And if this tension is real, we'll have a much better understanding. Okay, so I just want to end here. That's my time. Happy to take any questions. Thank you.
Thanks. Very nice talk. The results you showed of the different analyses of the Cepheid variable,
Yeah.
the group that was getting something on the low side.
This one or the reanalyses?
The reanalysis,
Yeah.
the Zhang et al. Is this because they were assuming there might be some redshift dependence in how the Cepheid variables behaved, or what exactly were they not doing that you guys did?
Right, yeah, so it's a pretty important issue. The question is, what did they not do? So basically, the whole idea of the distance ladder is that systematics can wash out. So let's say we messed up the luminosity of supernovae by 100%. That would, in effect, not change our value of the Hubble constant at all, because it changes supernovae in this rung, but also in this rung, and it cancels out. What that analysis did is they just looked at systematics in this rung and forgot about that there's any mitigation in this rung. So that will pull their mean value and also just blow up their errors at the same time. So that's really what was going on. But even so, their mean value is pretty close to ours. But it was just the errors that were fairly different.
Great, thanks.
Do one more question.
When you said that Gaia will crush the errors on the Cepheids, can you just be a little bit more quantitative? And also, what are the prospects for discovering? Do we need more Cepheids in the galaxy?
Right. Yes. The question is about I said Gaia will crush those. So basically, they'll. I think I show it here. So here we're using Milky Way parallaxes, and there's multiple. Every point here is its own Cepheid, and this is from parallax measurements. So Gaia will. There's maybe 10 to 20 points here. Gaia will produce about 1,000 of these with about 50 times better errors. So basically, this at least from the Milky Way, this will be locked down much better. So you're getting something like a factor of 1,000 times in this step. Right. So
I mean, the difference between long and short period Cepheids is an important difference. In
Right.
Milky Way, they're all short period Cepheids, and at large distance, they're all long period Cepheids.
Right. So so that's where the game comes in. So there will be some longer period Cepheids, but right. So a lot of them will be short period, and then the limiting question is that systematic of doing long period, short period. So right now that's not close to one of our biggest systematics, but right as we start pushing down the statistical precision, that becomes just a bigger and bigger issue. So that's exactly right.
All right, let's thank Dan again.